Point C in this problem is at the equivalence point. So we calculated it would require 27.5 milliliters of the titrant to reach the equivalence point. Mixing two solutions, so again, M1V1 equals M2V2 gives us our initial row in the ice chart. The initial concentration of the strong acid and the weak base have to be the same. That's the definition of equivalence. If these two numbers were not the same, then we wouldn't be at the equivalence point. Both of them run out at the same time. So we have 0 strong acid, 0 strong base left. We don't care about the bromide because bromide is not an acid and it's not a base. So all we have left is CH3NH3+, and we know that this cation is a weak acid because it's the conjugate of the weak base. However, this is not a buffer because we don't have any of the weak base. You need both components to make a buffer. So all we have here is the cation. And remember, at the equivalence point, the pH is controlled by the salt that's made. The salt, we have the cation and the anion, and we know that the cation reacts with water. So we have to do a second ice chart at equivalence. This particular salt has the cation that can act as an acid. It's a weak acid, not strong, so we write an equilibrium set of arrows, and we're going to produce hydronium and methylamine, the weak base. So the initial concentration of the cation is 0.2619. Pure liquid we can cross out. Hydronium and weak base are both 0. This reaction's in equilibrium, so we're going to get a minus x, plus x, and plus x. The K that we need is Ka, and again we got that from doing Kw divided by Kb, and the Ka is 2.27 times 10 to the negative 11. That would equal x squared over 0.2619 minus x. Very small equilibrium constant. Our x value is going to be negligible, so we can use the approximation to solve for x. X is 2.44 times 10 to the negative 6, and the approximation is valid. So when you look back at the ice chart, x is the concentration of hydronium, which means the pH is just the negative log of x, and the pH is 5.61. We're at the equivalence point, but the pH is not neutral. It was neutral when you had a strong acid and a strong base at equivalence. If one component is weak, remember, salts could either be acidic, basic, or neutral, and we know that this salt is an acidic salt because the cation hydrolyzes. The cation reacts with water, and it turns the water acidic. In another titration problem, if you had a strong base with a weak acid, we would have created a salt that's basic. So at the equivalence point, when one component is weak, the pH could either be acidic or it could be basic. It just depends on what kind of salt that the reaction makes.